You know, this quarantine hasn't been half bad. We've been able to spend all our time at the lake.
You're right, I love it up here. But it does kind of feel like we're cheating nature a little bit. I mean, this is a man made lake.
What?
A man made lake, just like a lot of the lakes up here in North Georgia. This used to just be the Tallulah River, but Georgia Power created this lake so that they could generate hydroelectricity.
Well, damn!
You're right about that, Daniel. These dams turn the movement of water into electrical energy to power homes in the area.
Wow, that's so interesting. Tell me more!
Well, okay, but just remember that at the end of this 10-minute video, you asked for it.
Alright!
Welcome to Abby's now 9.5-minute crash course of hydroelectricity. The first order of business, what exactly is hydroelectricity? Hydroelectricity derives from water, a renewable resource, meaning that it is easily replenishable in the environment. In a hydroelectric plant, gravitational potential energy is transferred into electrical energy as fast-moving water pushes a turbine that then generates electricity. To achieve this, dams are built along rivers to create a major water reservoir, usually a lake. A controlled amount of water is let into the dam through a control gate where the combination of the initial gravitational potential energy and the pressure caused by the reservoir causes the water to rush through a channel called a penstock and rotate a turbine. The water is then released at the bottom of the dam to continue on its path. The type of hydroelectric production I just described is referred to as conventional hydropower. Now, it is the most common form of hydroelectricity, but other areas have developed other systems to help harness the energy of water. Pumped storage hydropower is a slightly modified version of conventional hydropower. In a pumped storage system, electricity is produced to supply high peak demands by moving water between reservoirs at different elevations. The water moves through the system similarly to a conventional system. At times of low electrical demand, like in the early hours of the morning, the excess generation capacity is used to push water back into the higher reservoir. When the demand becomes greater, water is released back into the lower reservoir and through the turbine to generate electricity. Not all forms of hydroelectricity come from gravity, though. Tidal power and run-of-the-river hydropower also contribute to the energy that's generated in hydroelectricity. With tidal power, electricity is generated through the rise and fall of tides. As the tide comes in and out, the underwater currents spin turbines that produce electricity. There are very few locations that can use this form because there must be a very dramatic increase and decrease in the tide. This form is very predictable though, and in areas such as France have been found to be very successful. Run-of-the-river hydropower is a similar concept to tidal power. Run-of-the-river produces electricity through the flow of a river through a power plant. There's no reservoir to collect water, so any excess water passes through the plant without contributing to the energy production. Because water levels in rivers vary seasonally, run-of-the-river plants are not always a reliable source of energy production. Between these four types of hydroelectric energy production, approximately 1/6 of the world's power is produced, with a majority of it coming from conventional hydropower plants. Over the past couple years, as the environmental impact of fossil fuels has become more apparent, the frequency of hydroelectric power has increased drastically. Hydroelectric power does not harm the environment near as much as fossil fuels do. They are very powerful and relatively safe for people living in the area, much more so than, say, nuclear power. Hydroelectric plants also produce little to no waste or pollution, since water comes in, spins the turbine, and then goes back out into nature. Many power companies choose to pursue hydropower because the plants are very versatile in the amount of energy they can produce. The plants can simply let out more water to generate more electricity or store more water to produce less energy. Additionally, hydroelectric power is, in the long run, very cost efficient. After the initial dam is built, there is very little cost of upkeep, and as long as the dam has a stable supply of water, it should pay for itself relatively quickly and last a long time. Of course, hydroelectric power has its negatives too. When a company seeks to build a dam, they often displace the people who live near the rivers that become these lakes. Take Lake Burton, for example, a lake just north of where I am right now. When this lake was created, 200 people in the city of Burton were displaced. Many of their homes are still fully constructed at the bottom of this 120-foot deep lake. In addition to displacing people, these dams disrupt the natural ecosystem, displacing animals and killing natural plants. Even more dangerous, though, is the effect of a dam break, which could be caused by stress and fatigue on the structure of the dam. Though these are extremely rare, should a dam break, millions of gallons of water could crash on the surrounding ecosystem and have a cataclysmic effect. But compared to many other methods of energy production, the threat of a broken dam is infinitesimally small, making hydroelectric power one of the safest and most reliable forms of renewable energy production. That's a lot of information to throw at you at once. So, here's a 20-second intermission of my dog being the bestest boy. I hope that intermission gave you time to rub your eyes and get ready, because next we have to talk about math. So we're going to be calculating the power generated by hydroelectric dams. Oh, it looks like my friend Hydro Joe has come to join us. Not much if I'm honest, Joe. Quarantine's a bit of a drag. I mean, that's why I'm going all out in this physics video. I really don't have anything else to do with my time. But what are you doing here? That would be great. So Hydro Joe told us the equation we need to use, and as you can see, the type of energy being used to calculate the power is gravitational potential energy. Before we can solve some example problems, we need to break down the equation and figure out what everything means. The first variable, eta, represents the efficiency of the hydroelectric power plant. As much as companies try, it just isn't in the cards to have 100% of the energy going through the turbines transferred to electrical energy, affecting the overall power output of the system. The next variable is the power, which is measured in watts. On the other side of the equation, we start with the mass flow rate, or the mass of water that passes through a hydroelectric plant per second. This is measured in kilograms per second. This variable can also be written another way, as the mass divided by time. Another way to represent the mass flow rate is by multiplying rho, or the density of water, which is a constant, by v dot, or the volumetric flow rate. The volumetric flow rate measures the volume of water that passes through a hydroelectric plant per second. These are both just different ways of measuring how much water comes over the dam in a certain amount of time. The volumetric flow rate can be shown as the volume of water divided by the time. The next variable is the acceleration of gravity, or 9.81 meters per second squared. The final variable is the change in height of the water, also referred to as the head. The head is the height difference between where the water enters the system and where it leaves, which is not necessarily the height of the dam. So now that we understand the parts of this equation, we can do a practice problem. Hydro Joe, can you think of one for us, please? The Lake Rabun Dam has a head of 515 meters and can generate 15,000 kilowatts of power. With the plant working at 75% efficiency, what mass of water will have to run through the plant after a minute? So let's make sure we remember our equations and start to tackle this thing. For the information given, we will be using the first equation. We start by plugging in what we know. For the change in height, we plug in 515. For power, we plug in 15,000 kilowatts, which we have to remember to convert to watts, giving us 15 million watts. Now we have to plug in the efficiency, which is 75% or 0.75. After doing some amazing algebra, we end up with a mass flow rate of 2,226.77474 kilograms per second. That's pretty great, but not exactly what the question is asking. We need to find out the mass of the water that runs through the dam. So to do this, we need to remember the mass flow rate equation, which is the mass divided by time. We plug in the mass flow rate and the time in seconds, so 60 seconds, and algebra around to find the mass of the water that came through the dam. 133,606.4844 kilograms. That may sound like a lot of water, but in a dam as big as the Lake Rabun Dam, that's just all in a day's work. Thanks, Hydro Joe, for helping me out today. So there you have it. all the information I could teach you on hydroelectricity in 10 minutes. Not exactly sure what you're going to do with it, but hopefully you find something useful. Now I hope you are all surviving quarantine, and I can't wait to see you guys after all this is over.